In this video, we're going to look at solving trigonometric equations. All right, so to start with, we're going to be solving the equation, which means find all the solutions to the equation. Okay, so the first one is just to find where is tan x equal to 1. So you're going to want to have a unit circle handy for this. Okay. And when you're looking at this, even though x is really and you want to be in radian mode on your calculator. So we're looking for some number so that the tangent of that number is 1, but I think it's a whole lot easier to remember that that's basically an angle in radians. Okay. So then you can look at the unit circle, and you know that tangent is sine over cosine. So you're looking for places on the unit circle where the x and the y coordinate of the point is the same. So do you see how x would have to equal the pi over 4, and then leave a little room because we have to add something to that, or x could equal, in the third quadrant, you have negative square root of 2, negative square root of 2, and so that's 5 pi over 4. Okay, so those are basically the solutions within from 0 to 2 pi. Now, here's the thing. Tangent has a period of pi. What that means is the tangent graph kind of repeats itself, does this, every pi units. So you really aren't going to need to write this one on this particular problem where you're trying to find all the solutions to the equation. You can just take the pi over 4 and add in multiples of pi. And so when I write that n pi, that's where n is an integer. And then the idea is that if we let n equal 0, we'll get pi over 4. If we let n equals 1, we'll get pi over 4 plus 1 pi, which is 4 pi over 4, which will give us 5 pi over 4. You know, we can keep on like that, but we can also go in the negative direction, okay? And so I just want you to kind of think about, even though we're not doing these graphically, the whole point of 6-5 is to learn how to do this analytically. I want you to remember that, let's say that get my intercepts on here, my asymptotes, on here. Okay, so it would look something like that to start with. And let's say that this is the y-axis. Okay, so don't forget that you can also go and let n be -1. Integers are like -3, -2, -1, 0, 1, 2, and 3 on up. Okay, so it can be positive or negative. All right, so if you go in the negative direction, you can get to another solution by subtracting pi from that. Okay, and if you subtracted 4 pi over 4, you'd be at -3 pi over 4. All right, so you can't really list all the solutions. See, if you think back to the way we did this graphically, we're looking for all the x's that cause the tangent function to have a value of 1. So there's an x, there's an x, there's an x that would have a tangent of 1. And those aren't the only ones. You know, this keeps going. So you'd have infinitely many of them. And so you need to, oops, that's not a very good picture, that last one. So you need to be able to find all of these, or name all of those, and that's what we do with the n pi. Okay, so this would be the answer to that question. All right, so when you're doing tangent for tangent or cotangent, the period is just pi. So you're going to be adding, so you're going to add n pi, okay? All right, now let's look at this problem. So here we have a problem where what we need to do is rearrange things a little bit. So I'm going to subtract 3 sine x first off to try to bring my sines together onto one side. All right, when I do that, I wind up with 2 sine x equaling positive square root of 3. Got to get rid of the 2, so I'm going to divide by 2. and I wind up with sine x equaling square root of 3 over 2. Okay. All right, so now is when I go to the unit circle, or I can actually think about right triangles because I'm looking for the angle in radians where the sine would be square root of 3 over 2. Now, sine, cosine, and secant, cosecant, if you had any of those, dealing with any of those, the period is 2 pi. So you would add a multiple of 2 pi. We normally write it as 2n pi. All right, but we're not quite there yet. We got to figure out what the basic angle is. So you look at your unit circle now and you look for an angle that has the sine, which is the y-coordinate, being square root of 3 over 2. So that would be pi over 3. Let me do that in black. So x could equal pi over 3. But I need to keep looking because I also would have that happen at 2 pi over 3 and leave a little bit of room. Okay, because you got two spots within the unit circle within one rotation where you would wind up having the sine of those angles being square root of 3 over 2. And then what we'll do is we'll add 2n pi to each of them. And if they say they want you to solve the equation, or if they say find all the solutions, then this is what they're talking about, and you have to do that thing with the multiple, okay? All right, now, on the rest of the problems, we're going to be limiting ourselves to one rotation. So from 0, including the 0, all the way up to 2 pi. Oops, let me get that. I don't have this written, so that problem right there was supposed to be 2x. Okay, so here's an example where these are hard. These are probably the toughest ones, I think, where you have multiple angles. All right, so here's what you should be thinking. I need the tangent of some angle to be equal to the square root of 3, and you should think about that. So you go to the unit circle, and tangent is sine over cosine. So you should be looking for, so you should see that that would happen at pi over 3. Now, tangent has a period of pi, okay? So pi is the period. So when I'm looking at that, I don't need to keep going around the whole unit circle. When I find that the tangent of pi over 3 is equal to square root of 3, then what I can write is that I know this 2x would have to equal the pi over 3, would have to be that angle, okay? All right, now, at this point, there's several ways to think about it, but this is, I'm going to try to consistently do it this way because I think it's the easiest. But that could also be any n pi, any multiple of pi. So go ahead and put that in there, okay? And then solve this equation for x, because when you're asked to solve, you're looking for the x, right? So go ahead and solve that equation for x. So divide by 2 everywhere, okay? Then that's going to give you x equals, this would be pi over 3 divided by 2 would be pi over 6 plus n pi over 2. Now what you do is you let n equal 0, see what happens. Then your x would be pi over 6, wouldn't it? Because that n pi over 2 would just be 0. Let n equal 1, then x would be pi over 6 plus 1 pi over 2, which is pi over 6 plus 3 pi over 6, which is 4 pi over 6, and that reduces to 2 pi over 3. Now we could have seen that if we looked at our, well, I won't even go there. Let's just use this process. Okay, and then let n equal 2. If I let n equal 2, then that would be pi over 6 plus 2 pi over 2, which is pi over 6 plus pi, basically, which is 6 pi over 6, and that would give me 7 pi over 6. And you have to keep on. You have to do your n equals 0, 1, 2, until it doesn't make sense anymore, until you get past the boundary. You know, x had to be between 0 and 2 pi, and we're not there yet. So I'm going to go one more time. I'll move that other equation out of the way. Let me get it moved. Okay, so I'll go, let me see if I can move that down just a little bit. Okay, and then let me erase this so we have just a tad more room. And then we'll pick up from there. All right, so if n equals 3, we'll have x equals the pi over 6 plus 3 pi over 2, which equals pi over 6 plus, I'm trying to get a denominator of 6, so that's 9 pi over 6, which gives me 10 pi over 6, and that reduces to be 5 pi over 3. Let's see what happens if we let n equal 4. Sometimes these go on for a long time. That's pi over 6 plus 4 pi over 2. But you see how 4 pi over 2 is really 2 pi? That means that angle is going to be bigger than 2 pi, so I don't have to finish that one. Okay? All right, now what if we're doing a multiple angle, but it's like a fraction, like this one is sine of x over 3, and I've got it equaling a half. Okay, you still are going to think about what is the angle that has a sine of 1/2. Okay, and you know that that angle would wind up being pi over 6. 30-degree angle does that. Okay, but it also could be a half over there, like I'm thinking this in my mind. Look at the unit circle. There's one spot where the sine is 1/2, and then here's one where we have that reference angle that would also indicate that the sine would be 1/2, and that would be at 5 pi over 6. Okay, and I need to add in there, I need to move that over just a little bit. Let me rewrite that so I have more room. Okay, so x over 3 could equal pi over 6 plus multiples of 2 pi, or x over 3 could equal that spot, which is 5 pi over 6 plus multiples of 2 pi. So what we have to do here, kind of like when we divided by 2 in the previous example, here we have to multiply by 3 everywhere. So let me change my color to black. I'm going to multiply by 3, and I'm going to get x equals pi over 2 plus 6n pi, or x equals, let's see, what would that be if I multiplied by 3 everywhere? I'd still get that 6n pi, and then this would wind up being 5 pi over 2. Okay. All right, so let me see now. All right, so one of the things I just noticed is that 5 pi over 2 is 2.5 pi. It's bigger than 2 pi, so I'm not even going to consider that side at all. Then over here, I'm going to let n equal 0 and see what happens, and that's pi over 2 plus 6 times 0 times pi, so that's just pi over 2. Okay, and if I let n equal 1, I have pi over 2 plus 6 times 1 times pi. Oh, so that's too big. So you only have one answer to that question, and it's pi over 2. So like on the previous one, what happened there, it's hard to really think about all of this, but what happened there is the 2 that you see affected the period of the graph, so it kind of compressed everything. So more happened in less time. And so you wind up having a whole bunch of answers because you're pushing together those sine things. They happen more quick. I mean, those tangent pictures happen more quickly. Okay. And then the reverse is what's going on here. when you have a multiple that's fractional, it's like stretching the graph horizontally, so it doesn't complete one full cycle. It takes a lot longer to complete one full cycle, and so that's why you only wound up with this one answer. Okay. All right. Let me see. I think I'll stop the video there and start a new video for this next part.